Welcome to The Explainer, where we turn complex source material into clear, dynamic presentations.
We got our hands on this study guide for electrical engineers, and you know what? It's basically a secret decoder ring for the modern world. It's full of these questions that, when you really dig into them, they reveal the hidden forces that power everything from your phone all the way up to the entire power grid. So let's not think of this as an exam. Think of it more like a treasure map. Each question we solve is going to uncover one of the fundamental building blocks of our entire electronic world. All right, first things first. We have to start with the absolute most basic idea. I'm talking about the ground floor, the concepts that everything else is built on top of. And we get our first clue from question 16 in the guide. So it all kicks off right here. The source guide we have, which looks like it came from Korea, uses this term daejeon, and that translates to electrification. It's that simple yet profound moment when a material gets a charge, either by gaining or losing electrons. You know that little static shock you get from a doorknob? Yep, that's electrification right there. Now, a charge just sitting there is, well, it's interesting, but it's not very useful. The real magic, the thing that makes our world go round, happens when that charge starts to move. We call that flow current, and it's what does all the heavy lifting in our gadgets. And believe it or not, this flow follows a beautifully simple rule. And that brings us to a huge one, a core law from question 8, Kirchhoff's first law. The idea is actually super intuitive. Just picture a bunch of water pipes all meeting at one point, right? The amount of water flowing in has to be the exact same amount that's flowing out. It can't just vanish. Well, it's the same for electricity. At any junction in a circuit, the sum of all the currents is always zero. Nothing gets lost. It's a perfect, elegant conservation law. Okay, so now we get how charge flows. Let's look at the three big players, the main components engineers use to control it, to store it, and to slow it down. All right, first up from questions 2 and 19, we have capacitors. The easiest way to think of them is like tiny little charge buckets. They're like super fast batteries that store energy. Now here's the cool and kind of weird part. If you line them up side by side, that's in parallel, their storage capacity just adds up. Simple. But if you connect them end to end, in series, their total capacity actually goes down. A little counterintuitive, right? Next up, we've got inductors. Now, if capacitors are charge buckets, inductors are more like heavy flywheels for the current. They're just coils of wire, really, but their whole job is to resist any change in the current's flow. And question 15 points out something really amazing. When you put two of these coils near each other, their magnetic fields start to talk to each other. This mutual inductance, that M in the formula, can either give their combined power a huge boost, or if you flip one around, it can almost completely cancel them out. Okay, so we have these components. Now let's connect them to one of the most powerful and frankly magical relationships in all of physics, the link between electricity and magnetism. So question 13 from the guide is clever. It teaches us the rules of magnetic fields by asking us to spot the fake rule. These lines of force, they're like an invisible framework for the universe. They always go from north to south. The closer they are, the stronger the field. And they even act like stretched rubber bands, always trying to shorten. But the biggest rule, the one that's non-negotiable, they never ever cross each other. And this is where it all comes together. Question 1 brings in Fleming's right-hand rule. And this is basically the blueprint for every single generator on the planet. If you have a wire and you move it through a magnetic field, boom, you create electricity. And this simple hand gesture shows you exactly which way that current will flow. It's motion, magnetism, and electricity all locked together. And just when you think you've got it all figured out, question 14 throws in this little twist called Lenz's law. And what it says is that electricity is, well, it's a little bit rebellious. The current that you induce will always create its own tiny magnetic field that pushes back against the very thing that created it. It's like nature's way of saying, hey, for every action, there's a reaction. It keeps everything in balance. So we've got the pieces, we get the forces. Now let's get down to business. Let's see how engineers actually measure all this stuff, how they calculate the real power in these systems. Question 5 gives us a really practical problem. You've got an inductor. Remember, just a coil of wire, and it has stored 25 joules of energy. The question is, how much current did it take to cram all that energy in there? Well, lucky for us, the relationship between the energy stored in that coil, its inductance, and the current flowing through it is all wrapped up in this neat little formula. We know the energy and we know the inductance from the problem, so all we have to do is plug them in and solve for our mystery current. And what do you get? A nice, clean 5 amps. Now, the math itself isn't the big deal here. The crucial takeaway is that this is math. It's a predictable, direct relationship. You can calculate the energy from the current and the current from the energy. No guesswork involved. And then question 4 hits us with a huge design principle. This is key for, well, for everything. If you want to squeeze the absolute most power out of a source, like a battery or your wall socket, you have to do something called impedance matching. You have to make sure the resistance of the thing you're powering perfectly matches the internal resistance of the power source itself. It's this perfect state of balance that gives you maximum efficiency. Okay, for our last section, let's zoom out a bit. Let's look at the actual shape of these electrical signals and see how all these different components play together in the real world. Question 12 shows us something really cool. You know those jagged, complex-looking electrical waves you might see on an oscilloscope? They look chaotic, but they're not. Any one of those messy waves is actually just a simple recipe. It's a combination of 3 basic things: a steady, flat DC voltage, one main fundamental wave, and then a bunch of smaller echoes of that wave called harmonics. Engineers even have a name for this. It's called the form factor, and we see it in question 10. It's a single number that basically tells you the shape of an AC wave. You just divide its effective value by its average value, and bingo. You get a single number that's like a shorthand for how pointy or how flat that wave is. And finally, when we put all 3 of our main components together, the resistor, the inductor, and the capacitor, in one circuit, something magical happens. Question 11 points this out. There's this one special frequency called the resonant frequency, where the push from the inductor and the pull from the capacitor perfectly cancel each other out. And at that exact sweet spot, the total opposition of the circuit, the impedance, just drops to its absolute minimum. This lets the current flow like crazy. And by the way, that's exactly how your radio tuner works. So think about what we just did. Just by decoding a handful of questions from an engineering study guide, we've basically pieced together the entire story of modern electronics. It all starts with a simple idea of charge. That charge is then steered and controlled by a few key components. And all of that is governed by the beautiful and totally unbreakable laws of electromagnetism. And here's the most important part. These aren't just rules in a textbook. This isn't just for an exam. This is the operating system of our world. It's humming in the walls around you right now. It's firing away inside the device you're watching this on. So that leaves us with one final thought. These rules built the world we have today. What are they going to empower us to build next?